Greetings. In this video I'm going to prove the Meyers-Serrin theorem, which says that functions in Sobolev space may be approximated by smooth functions. Sobolev spaces, usually denoted WMP, consists of functions with weak derivatives up to order m, all of which are integrable to degree p. There is, of course, over an open set omega of Euclidean space. Here dk stands for a partial derivative, an arbitrary partial derivative, where k is a multi-index, and so k1 up to kn are non-negative integers. And weak derivatives are defined by analogy with the integration by parts formula. So given a function u, which need not be differentiable, if there exists some function which we call dku, such that this formula is valid for any smooth function phi with compact support, then we say that dku is a weak derivative for u. Then it follows from the integration by parts formula that if a function is differentiable, then its weak derivatives are just its usual derivatives. And Sobolev spaces are normed vector spaces. The Sobolev norm being just the sum of the LP norm of each of its derivatives. So in the time that Meyers and Serrin were writing in the 60s, in the theory of partial differential equations, analysts would deal with so-called H-spaces, which were defined as the closure of the space of smooth functions with respect to the Sobolev norm. And they knew that for simple enough domains, these spaces would coincide. So what Meyers and Serrin did was to prove that they coincide in general, irrespective of the domain omega. In order to gain a better appreciation of the construction of Myers and Serrin, let's first consider the case where the function is defined over the entire Euclidean space. In that case, all we have to do to approximate the function is to apply the mollifier operator, which is defined by convolution with a certain smooth function with compact support phi epsilon, which we are going to define in a second. But this is simply convolution, and d mu, of course, is the element of volume, the integral being taken over the whole Euclidean space. There are many choices for this function phi epsilon, all of them having to satisfy the condition that its integral is equal to 1. But the standard mollifier, which is arguably the simplest one, is constructed as an exponential function. So it's equal to this exponential if x lies between, if x is inside the unit pole and 0 otherwise. Note that this is in fact a smooth function, and since here when we have the norm of x equal to 1, we have 0 in the denominator, and thus we have exponential of minus infinity, which gives us 0. Otherwise, the norm of x is less than 1, so is its square. So we have a positive number in the denominator and a negative one in the numerator. So it's always the exponential of a negative number. And the actual phi epsilon is defined as epsilon to the minus n multiplied by phi of x over epsilon. So this phi epsilon satisfies this property because we can reduce their integral to the integral of phi by a change of variables. Namely, we just take the new variables x prime to be x over epsilon. And so this implies that the element of volume, the new element of volume, is just the old element of volume divided by epsilon to the nth power. So these terms together give us the new element of volume, and we just have integral of phi d mu, which is just 1 if we define C appropriately. Namely, C is just the reciprocal of the integral of this exponential. So now we should verify that this u epsilon, which will be our approximation, is actually a smooth function, since we want to approximate u by a smooth function. And to do this, it will be convenient to write this convolution as the integral of phi epsilon of x minus x prime multiplied by u of x prime by a change of variables. And so what will happen is that when we differentiate with respect to the x variables, we'll differentiate the smooth function phi epsilon, and this will always be possible, so u epsilon will indeed be smooth. More precisely, let's consider the partial derivative with respect to xi of u epsilon Now, since the integrand as a function of x is smooth, we can take the derivative inside, and now we can just repeat the argument. That is, by induction, we'll deduce that u epsilon is smooth. But furthermore, we can relate the derivatives of u epsilon to the weak derivatives of u. First, we note that by the chain rule, we have for any function of a difference, the derivative with respect to the variables that are being subtracted are simply the negative, the opposite of the derivatives of the variable with respect to the various variables that are being subtracted from. So if we apply this here, we obtain minus the integral of the derivative of phi epsilon with respect to x prime I multiplied by u. And now we can use the definition of weak derivative, which will give us that this is equal to the integral of phi epsilon multiplied by the weak derivative of u with respect to x prime I. And now, comparing the first and last members, we have that the partial derivative of u epsilon with respect to the ith x variable is equal to the convolution of phi epsilon with the corresponding partial derivative of u, that is the corresponding weak partial derivative of u. And we can generalize this by induction to obtain that an arbitrary partial derivative of u epsilon is the result of applying this mollifier operator to the corresponding weak derivative of u, provided that the weak derivative actually exists. That is, provided its order is not greater than m. So now that we have shown that u epsilon is indeed a smooth function, and we have shown what are its derivatives, we must show that it in fact approximates the given function u. First, we should verify that u epsilon of x goes to u of x at almost every point as epsilon goes to 0. It will be convenient to exploit the fact that the integral of phi epsilon is equal to 1 in order to write u of x as the integral of phi epsilon of x prime multiplied by u of x d mu prime, or which is the same, the integral of phi epsilon of x minus x prime multiplied by u of x d mu prime, because then the difference u of x minus u epsilon of x becomes the integral of phi epsilon of x minus x prime multiplied by the difference u of x minus u of x prime d mu prime. So we have to bind this. And of course, by monotonicity of the integral, this is not greater than the integral of the absolute value. And now we observe that since phi epsilon has support the ball with radius epsilon, we may restrict the domain of integration to be exactly this ball. Now we may write phi epsilon in terms of phi and use the fact that phi is bounded. Now, this function is locally integrable since u is integrable to degree p. And so it follows from the Lebesgue differentiation theorem that this goes to 0 for almost every x. In fact, one weaker formulation of Lebesgue's differentiation theorem can be interpreted to mean that if u is a locally integrable function, then it's continuous on the average. And we can see here that we're taking some kind of average, or rather a constant multiple of an average, since we're integrating over a ball of radius epsilon and dividing by epsilon to the nth power, which is proportional to the volume of the ball. Now that we have pointwise convergence almost everywhere, we may try to dominate u epsilon by a function integrable to order p, and then use Lebesgue's dominated convergence theorem to conclude that u epsilon converges to u in the LP norm as well. And since we have seen that the partial derivatives of u epsilon up to order m have the same relation to the weak derivatives of u as u epsilon has to u, if we prove this, then the same will apply to each of the weak derivatives of u up to order m, and will then automatically conclude that u epsilon converges to u in the Sobolev norm as well. So all we have to do now is to dominate u of epsilon. And a good guess would be that u epsilon is dominated by u itself. And we'll see that this is indeed the case by a clever use of Hölder's theorem, since u epsilon by definition is equal to the convolution of phi epsilon with u, we may attempt to apply Hölder's theorem here. But the thing is that the family of these phi epsilon does not have a uniform bound, and applying Hölder's theorem directly won't do. What we actually have to do is to break phi epsilon into two factors. Now we can apply Hölder's inequality, separating the integrand like that. So this, by Hölder's theorem, is not greater than the first factor corresponding to this factor of the integrand will be put in the LP norm. So this integrand in the first factor will be raised to the pth power, and in this factor we'll have the LP prime norm, where P is the conjugate, where P prime is the conjugate of P. So the relation between P and P prime is that the sum of their inverses is equal to 1. In other words, 1 over P prime is equal to 1 minus 1 over P. But then here we have P prime times the difference, 1 minus 1 over P. And so this is equal to 1. And thus, by the defining property of these mollifiers, this whole term will turn out to be 1. So now we have the integral of u epsilon, its absolute value raised to the pth power, is not greater than the integral of phi epsilon of x minus x prime times the absolute value of u to the pth power d mu prime d mu. And now we may exchange the order of integration and integrate over the x variables first. And when we do that, we'll get precisely the integral of the absolute value of u to the power p. Thus we can use Lebesgue's dominated convergence theorem to conclude that u epsilon converges to u in the LP norm, and consequently u epsilon converges to u also in the Sobolev norm. And here, of course, we have only dealt with the case where P is finite.